Hey everyone, in this video we're going to be talking about expressions and formulas. So there's a few formulas that are pretty important. We have the Pythagorean formula. We've discussed rate, distance, and time formulas at this point. We're also going to be talking about combining like terms and converting verbal expressions into mathematical statements. So a whole bunch of topics coming up in this video, and if you'd like to jump to any particular topic, you can always click on any of these links over here on the left side of the video at any time to go to that portion of the video. So to begin this video, let's take a look at some definitions. So I'm going to be talking about equations, and I'm going to be talking about formulas quite a bit, so it's good to know exactly what I mean if I use a particular word. So an equation is the statement that two expressions are equal to each other. So for example, if I say something like 3x plus 1 is equal to 4x minus 3, if I say something like this, the 3x plus 1 is considered to be an expression. It expresses any number you would like. Okay, so it just expresses something. And the same goes for 4x minus 3. This is an expression of anything you'd like it to express, really, any particular number. So it expresses something, and 3x plus 1, it would express the same thing because here we have an equality between these two expressions. And when we have an equality between two expressions, so this is saying 3x plus 1 is equal to 4x minus 3, that's what creates an equation. Okay, so it's very common for people to think that, mathematicians are always working with equations, but, that's not necessarily the case. A lot of the times you may just be working with an expression to show that this equals something else, but we're not always working with the equations, but when we have two expressions equal to each other, that's when we have the equations. And moving on, we have formulas. So formulas show how one variable depends on other variables. Okay, so this is a little bit different than an equation. Now, all formulas are equations, but not necessarily all equations are going to be formulas. Okay, formulas in particular show, again, how one variable depends on other variables. So for example, one formula we've discussed in earlier videos was that rate is equal to distance over time, or average rate is equal to the distance traveled over the time it takes to travel that distance. So this is one particular formula. This shows how rate is dependent upon the distance and the time. Okay, so, and again, you can see that the formula, the rate here, the r, this is an expression, and this equals d divided by t. D divided by t by itself is another expression, so an expression equal to an expression, it's an equation. And that's the case for all formulas. All formulas are going to be equations. Another formula we've discussed was if we're talking about triangles. So if we're talking about triangles, we know the area of a triangle is equal to half the base times the height. So this is another formula. The area is dependent upon the base and the height, which are other variables. Okay, so that's another type of formula. In any area formula that we had, they're all going to be formulas. So it's good to keep those definitions in mind. When I say expression, I'm just talking about a statement that expresses some number. When I talk about an equation, I'm talking about when two expressions are equal to each other. And when I talk about formulas, I am probably referring to, something like this. Something you're going to have to keep in mind for future examples, like the rate, distance, time problem here. Now, Let's talk about this toothpick example here. So on the left side I have toothpicks. You're probably wondering what that means. So the toothpicks I have here represent a certain pattern. And we may want to find out some information about this pattern here. And so what we're going to do is we're going to create a formula from this pattern we see. Okay, that represents the total number of toothpicks in any given case here. So these squares that I drew here, these all represent toothpicks. Each side of the square is a single toothpick. So when I make one square, I need to use 4 toothpicks. When I make 2 squares, well, here's my first square, and then I could just join it with 3 more toothpicks so that you'll see 2 squares here. And you'll see I need 7 toothpicks in all to do that. To make 3 squares, I would need to put on 3 more. So I'm going to have 10 toothpicks to have 3 squares. And to have 4, I need 13. And to have 5 squares, I need 16. So we want to create a formula for the total number of toothpicks depending upon how many squares we want. Okay, so if I wanted 3 squares, you would have to tell me how many toothpicks immediately without drawing these pictures. Okay, let's just say we want an algebraic formula here. So we may notice, to help us out with this formula, there's going to be a lot of right answers for this too, so you may want to try it before I actually go through this here. But to create formulas, one thing you may want to keep in mind here is to take a look at what kind of answers you're getting here. First we get 4, then we get 7, right? That's a difference of 3 here. So we added 3, 4 to 7, and we added 3, 7 to 10. So every square we add beyond the first one, we're adding 3. Okay, so adding 3 and adding 3 and adding 3 and so forth. So, that may help out with the formula. So, the total number of toothpicks. So remember, repeated addition is multiplication here. So if we do 3 times the number of squares, okay, so total toothpicks equals 3 times s, the total number of squares. Will that tell us how many toothpicks we need? Well, let's see. If we have 1 square, this will say 3 times 1 is 3. So we would need 3 toothpicks for 1 square. Is that right? Well, no, because for the first square, we see we want 4 toothpicks. So we're off by 1, right? So we may want to add 1. And let's see what happens. Well, if we have 1 square, we have 3 times 1 plus 1, we get 4 toothpicks. So that's correct in our pattern here, right? If we have 2 squares, so let's see, T2. So if we have 2 squares, this will be 3 times 2 plus 1 is equal to, so this says we need 7 toothpicks, is that right? Yep, that's right. And for 3 squares, we'd have 3 times 3 plus 1, following that formula. That's 9 plus 1, that's 10. Okay, so this says if we have 3 squares, we would need 10 toothpicks. Okay, so this formula works out just fine. The total number of toothpicks needed is dependent upon the number of squares that we have. That's one example of a formula. And this is one way to represent that formula. There's going to be other ways to represent this formula as well. For example, we could say, all right, if we want a new formula, you may say, so we're starting with 4 toothpicks. So let's say 4 plus, and then for every square we add, we're adding an additional 3 toothpicks, right? So this will be 3 times s. Now, I know that if I have 1 square, I'm going to want an answer of 4. Okay, so this says to me that when s is 1, I need this in parentheses here to be a 0. So this would be 4 plus 3 times 0 when s is 1, right? It may take a while to think about. Don't worry if you're a little bit confused at that point. But if I didn't have this minus 1 here, when I have 1 square, this would say, well, you would need 7 toothpicks. But I'd essentially be one piece of information ahead of where I should be. So that's why I need to subtract this 1 here. Okay, so let's see. When I have 1 square, this formula says I would need 4 plus 3 times 1 minus 1. Now 1 minus 1 is 0, following the order of operations in parentheses first, right? And then 3 times 0 is 0, plus 4 is 4. And that's what we want, right? 4 toothpicks when we have 1 square. And let's just check the next one really quick. If we have 2 squares, this will be 4 plus 3 times 2 minus 1. This is equal to. Now, order of operations, again, we have parentheses first. 2 minus 1 is 1. And 3 times 1 is 3. And then 4 plus 3 is going to give us 7. Okay? And that's what we want, right? If we have 2 squares, we should get 7 toothpicks. So we see that this formula is also correct. So, and they look really different, right? 3 times s plus 1, and this one's 4 plus 3 times the quantity s minus 1. So that's pretty different. So let me go up here and let me just check here. So if both of these formulas work, then they should be equivalent expressions. Okay, and if we have equivalent expressions, we could write an equation between them. 3 times s plus 1 should equal 4 plus 3 times s minus 1. So let's see. Over here on the left side, I can't simplify this here on the left side. So let me work with this expression here. 4 plus 3 times s minus 1. Let's see. Let's try to simplify this statement, and let's see if it actually equals 3 times s plus 1. So we have a 4 plus, and now we have the distributive property here. 3 times s is 3s, and 3 times negative 1 is negative 3. Okay, and now 4 minus 3 is 1, or 4 plus a negative 3, however you want to think about it, is 1, and we have a plus 3s right here. So up here we have 1 plus 3s, right? It doesn't matter which order you do addition, right? That's commutative. It doesn't matter the order in which you do something. That's not true for everything, but it's true for addition anyway. And this statement we saw equals 1 plus 3s as well. So we do see that these formulas are in fact equivalent. Okay, so let's move on. Let's talk about combining like terms here. So here I've written down combining like terms. If we have something like 2s, right, and s in the previous case was representing squares, right? So if we have 2s and s, these are called like terms because they contain the same variable. Okay. Now the variable in this case is s. This has an s, and this expression here also has an s. Okay, so these are considered to be like terms. If we had something like s squared and 4s squared, these are like terms as well because s squared and s squared are the same. Okay, they also need to have the same power. Okay, like here the power is 1. So keep a lookout for that. If they have different powers, then they may not be like terms. Now, you could often make something look like something else in mathematics when really they're the same. So I say most likely they're not like terms, but in rare instances they may be. But really what you're looking for is that they have the same variable and they should be to the same power. And that'll make them like terms. So now I have a new definition here. The coefficients are the numbers in front of the variable. Okay, so I'm going to be using the term coefficients quite a bit. So like in this case here, when we have 2s and s, the coefficients, okay, so we have 2s, and essentially what we have is 1s. That's a special property of 1, right? If you have a 1 times something, it's not going to change that something. So the coefficients in this case would be 2, and in this case here, the coefficient is 1. Okay, so again, it's the numbers in front of the variable. And in this case here, the coefficient of s squared is a 1, and the coefficient of 4s squared is a 4. Okay, those numbers in front of the variable. Now, the shortcut for combining like terms is to add the coefficients. And if you notice, I put shortcut underlined 4 times here, just to emphasize the fact that when we do combine like terms, adding the coefficients or combining those coefficients together is most definitely a shortcut. So let me show you what I mean. So if we have 2 times s plus s, okay, and we want to combine like terms here. Now in all practical cases, we would apply this shortcut, okay? I mean, once we know what we're doing, we could use the shortcuts to bypass, a lot of minutes of extra work here. So 2s plus s, you may already know it's going to be 3s, right? But now this arises really from a combination between a lot of properties in mathematics. Okay, and it's only through these properties that we gain the ability to use these shortcuts. Okay, so let me show you what I mean here. We have 2s plus s. Now, through the special property of 1, I could write a 1 right here in front of the s without any penalty, right? It's still the same thing. Now, through the reverse of distribution, or actually you could say through commutativity. Multiplication is commutative, meaning you could reverse the order. Instead of writing 2 times s here, you could just as equally say, you have s times 2 plus s times 1. That wasn't necessary, but we could write it like that if we wanted to. Through the reverse of distribution, we could say, okay, since this expression and this expression both have an s, we could factor out an s. And I didn't talk about factoring yet, but factoring is the reverse process of distribution. And so when we factor or reverse distribute, we have a 2 left over and a 1. Okay, so this is s times 2 plus 1. And now we could do the addition inside of the parentheses here. 2 plus 1, we get 3. Okay, and again, through commutativity, s times 3 is the same as 3 times s. Okay, so there's a lot of properties involved really in adding these two expressions together. However, you'll see our final answer, we get 3 times s. All we needed to do was take this 2, that's the coefficient of that s, and the coefficient of this s is a 1, so we add the 2 and the 1 together, we get the 3, and we just keep the variable the same, s in this case. It's like 2 squares plus 1 square. How many squares do you have? You have 3 squares, right? Okay, so that is combining like terms. So let's take a look at some few examples I have here. So we want to simplify by by combining like terms. So the first one, A, 5x plus 9x. We have the coefficient 5 and the coefficient of 9. X and x are certainly like terms, so we apply the shortcut, add those coefficients together, and keep that variable the same, so we get 14x. The same case for B. Y and y are both considered to be the same variable, so we have like terms here. So we can combine the coefficients. Now on the previous page, I think I said, you would be adding the coefficients, but in this case, subtraction. You could think about this as adding a negative. So anyway, you want to combine the coefficients. So in this case, we have a 2 and a negative 3. So 2 plus negative 3 is negative 1, and we keep that variable the same. Now for part C, we have a mix of different things here. So in this expression, we have a 3a, a 6, a negative 2a, and a 9. So first of all, we want to locate the like terms. So 3a and negative 2a are like terms, and a 6 and a 9 are considered like terms. Now those are both constant numbers. Before we start throwing in all these variables, you probably would have just added the 6 and the 9 anyway, right? Because that's simple to do. But once we start introducing a lot more ideas, and give you a lot more tools to work with, things start to become a little less obvious, because sometimes we tend to overthink things if we have too many tools at our disposal. But we never want to forget the basics. So the basics would say if we have a 6 and a 9, we're going to combine those to get 15. You could also think about a variable being here to the 0th power. That's another way to see that they would be like terms. But now let's combine these. We have a 3a and a negative 2a. So that gives us 1a. Now I don't need to write the 1, so I'm not going to bother. And then 6 and 9 will give us a positive 15. So we get a plus 15. Now in part D, it's similar to part C. Our x squared terms here, those are like terms. And then x to the first powers, those are going to be like terms. So we want to combine these two, and we want to combine these two. So 3x squared plus 2x squared, we want to go ahead and combine those coefficients to get 5, and our variable is x squared. Next up, 3x minus 9x, we do 3 minus 9 to get negative 6, and then we keep our variable the same. Okay, so that's part D. Now part E, we have part E, F, and G. We have some fractions to work with. Now, there's no reason to be afraid of these fractions here. It's still the same process as before. We're trying to find a common denominator and then combine the numerators somehow and keep the common denominator. So in part E, we have a common denominator already. This is x, and x. That's fine. So the numerator would be 3 minus 2, which is 1, and then we keep the common denominator, which is x. Now, it's fine if you leave your answer like this. I just want you to recall that 1 over x is the same thing as x to the negative first power. So you could either write it like this, or you could write it like this. These are the same statement here. Now in part F, a over b plus 7 over b. We already have a common denominator, so that's fine. We combine the numerators, which is no way to do, right? A and 7 are not like terms, right? We have an a here and a 7 here, so there's no way to combine those. So we just leave it like that. And then we have our common denominator, which is b. So that would be the final answer there. Now, part G, it looks a little bit rough, right? There's a lot going on in part G. So let me go ahead and rewrite this here. We have 1 over x plus x, and then plus x squared. Now, instead of writing x to the negative first, remember x to the negative first is 1 over x. So in order to know this, we'll need to recall that a to the negative n is 1 over a to the n. So x to the negative first, instead of writing this, it should be 1 over x to the positive first. But anything to the positive 1, you don't need to write it. And then plus, here we have 1 over x squared. Okay. So, now there's actually no nice way to write this particular expression here. There's a lot of ways you could think about writing it, but like we may want to try combining 1 over x and 1 over x, and then we could combine the rest. But let's try to combine this all into a single fraction here. So this is over 1, and this is over 1, right? So it looks like our common denominator here would be x squared, okay? All of these pieces go into x squared. That's the highest piece here. So in order to get an x squared here, we'll need to multiply by x. And balancing the numerator, we do the same thing. Here we would need x squared. Here we would also need x squared. And here we would need an x. Okay, so there's a lot of things here I didn't get to talk about yet in videos, so I wouldn't worry too much about what's going on here. So okay, let's continue this one, but this is going to be x over x squared, and this will be x squared times x is actually x cubed, and this is over x squared, and x squared times x squared is x to the 4th over, that's x squared, and this will be x over x squared, and this is 1 over x squared. So we would then combine this, so I ran out of room pretty much, but we would combine this into a single fraction, which would be, we have these two, these are like terms, x and x, we get 2x, and then we have plus x cubed, x cubed plus x to the 4th plus a 1, and the common denominator would be x squared. So now I don't like that example too much. I don't know why I had it here, but if you're able to follow along in that example, that's really good. But if not, I really wouldn't worry about this one too much. Okay, so that's combined like terms. Those are the basics for that. Now let's move on to the next topic here. We have algebraic and verbal expressions. So this we came across a little bit in previous videos already. Algebraic and verbal expressions. So what we want to be able to do is we want to be able to take verbal expressions and translate them mathematically into some type of algebraic statement so that we could work with it easier. Okay, so I have an example here that will allow us to do that. We could translate this into some math statement. So the height of a parallelogram is 5 inches less than the base. So we want to find the area of the parallelogram when the base is 20 inches. Okay, so when dealing with verbal expressions, if it is at all possible to draw a picture, I would most definitely recommend doing so. It's very helpful to draw a picture. So we're talking about parallelograms first of all. So let's go ahead and translate that into, let's get a nice parallelogram here. Okay, so something like that will do. All right, there's my parallelogram. Now, we see that we have the height of the parallelogram. Now, you need to recognize where the height of a parallelogram is. You need to recall that the height is going to be from here to here. Okay, really, you could draw it anywhere you'd like. I mean, from the top base and draw a perpendicular line down to the bottom base. That's going to be the height. Typically, when I draw the height of a parallelogram, I draw it over in this corner. But really, anywhere from the top to the bottom will be the height. Okay, so this is the height. Let's call that h. Now, we have the height is. Now, this is translates to an equal sign. Okay, so whenever you see is in a verbal expression, we want to translate that to an equal. So height is. Now 5 inches less is another key term here. 5 inches less than the base. Okay, so how can we translate that? 5 less than the base. Now, we do know what the base is. We know the base is 20 inches, but let's pretend like that's not here at this point. Let's just say the base is B. So here's the base, B. Now, 5 inches less than the base is going to be B, and then 5 less would be minus 5, right? So the height is 5 less than B. Okay. A common mistake is for people to translate this as h equals 5 less than the base. Okay. That is not correct. We don't want to read less than as being subtracting the next portion. If we read 5 less than the base, we have to think about where how the order is going to be, because subtraction is not commutative, unlike addition or multiplication. So we don't want to make this mistake, so be careful of that. So think carefully before you write down your formula. Okay, now we have h is 5 less than the base. Okay, so looks like we have all the important information translated. Now we want to find the area of the parallelogram when the base is 20 inches. Okay, so first of all, what is the height? We know h is b minus 5, and we know b is 20, so that would make the height 15 inches. Okay, and the base, they tell us, is 20 inches. We don't need to do any work for that. Okay, so now we need to recall the formula for the area of a parallelogram. The area is going to be the base times the height. Okay, and this is equal to 20 times 15, which is 300. And don't forget the units down here. Since we're talking about an area, this is a two-dimensional measure. So that means our units are going to be squared. So this should be 100 square inches. And even though I say it's square inches, you write the exponent after the inches here. So 300 square inches is the area of this parallelogram. Okay, so that's one example of how we translate these verbal statements into mathematical expressions and formulas and equations. Now, next up, we want to go ahead and talk about the Pythagorean Theorem. So this is a very famous theorem, right? This is coming up in this particular video here because we're talking about formulas, and the Pythagorean Theorem happens to be a very famous formula. Now, it's named after the Greek philosopher, mathematician Pythagoras, and he lived around 500 BC or so. But it's well known that the Babylonians and the Egyptians and the Chinese all knew the Pythagorean theorem approximately 1500 years before Pythagoras did. But the reason it's named after Pythagoras is because he was the first one to actually, we think anyway, pending any historical finds, we know that Pythagoras was the first one to prove this particular theorem. So the prior mathematicians, they did know that this formula worked, but we didn't see any reasoning from them as to why this particular theorem worked. Now, I could show, there's maybe over 1,000 proofs at this point of why the Pythagorean theorem actually works. And I could show you a couple, but they take a while and they might be out of the scope of this video. So I don't know, we'll see. So Pythagorean theorem, what is it anyway? So for right triangles in particular, and this is key, I have the term right triangles underlined here. This theorem will only work for right triangles, meaning we have a triangle here, and one of the angles in the triangle is a 90-degree angle. Okay, there's lots of different kinds of triangles. You have the isosceles or equilateral. The Pythagorean theorem is not going to work for those particular triangles. Okay, and the Pythagorean theorem says that a squared plus b squared is c squared. So it's common to think that a and b could be any side of the triangle, but really a here is called a leg of the triangle, b is the other leg of the triangle, and c is the hypotenuse. Let me try to spell that correctly. Okay. So c is the hypotenuse of the triangle. So the hypotenuse of a right triangle is always going to be the longest side of the triangle. Now, this formula says that one of the legs squared plus the other leg squared is equal to the hypotenuse squared. Okay? So we can't jumble this formula around. We can't say something like c squared plus b squared is a squared. Okay, that's a common mistake. If people are given two parts of the triangle, they automatically think that this is how the formula should be written. Now, if you were given two sides of a triangle, you can use the formula, but you have to make sure you put the information in the correct spot. Okay? So this is typically how the formula is written. A squared plus b squared is c squared. Now, I do have an example coming up, so if you'd like to see that example, I would encourage you to go ahead and click on that example. But let me show you a quick demonstration of why the Pythagorean theorem actually works. And this is thought to be what Pythagoras might have used to prove this particular theorem. So we're going to start with, and this is an easy proof. Anybody with the concept of area could understand this proof here. So we're going to begin with a square here, and let me mark some things off here. So let me mark a B. So the distance from here to here is B. Let me make that same demarcation here. This will be A, and since this is a square that I'm making, this will also be A. now I want this here. Let me mark the location B. Here to here is going to be B. This will be A. From here to here is going to be a distance of A, and this will be B. Okay, so this is a square first of all, right? All the sides of the square consist of A plus B, A plus B, A plus B, and so forth, okay? So convince yourself first of all that this is in fact a square. Okay, and let me just do this freehand here. So we have this corner. So that square is little b squared up there. And let me make a little square down here. So this squared is a squared. So the area of this squared is b squared, right? And the area of this squared here is a squared. And the area of this rectangle here is a times b. And the area of this rectangle here is a times b. Okay? So we have a statement about the area of this entire square. Now let's draw another square over here and let's compare the two. Let's draw the same square. Okay. So here is my other square. Now, in this case, let me draw B, and this will be A, and this will be B, and this will be A, and then from here to here will be B, and then this portion will be A, and from here to here will be B, and this portion here will be A. Okay, now let me draw the lines between these markers here. So first of all, do we have the same square? All four sides of this square are a plus b, a plus b, a plus b, a plus b, right? Those are all the same. So let me draw a new picture inside of here. Okay, I'm just connecting all of these markers that I put. Oh, that's a bad one. Okay, so let me go like this right here. Okay, so we're almost complete. It'll take about another minute. So what we're doing here now is we have these four triangles here. We have a triangle here. Oops. We have a triangle here, 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 and here, right? These are all right triangles. Now, what's the area of this triangle here? Well, this would be half of the base times the height. Okay, and you could call the base B, the height A. That would be fine. So this would be 1/2 AB. And the same thing with here. Half the base times the height, that's the area. 1/2 AB. And this is 1/2 AB. And this is 1/2 AB. Now what about this square in the middle? I don't know the length of these hypotenuses here, but this is C here, and from here to here is also C, and this will be the same, and this will be the same here. Okay, so from here to here is the same as here to here, same as here to here, and so forth. So if I call all those sides C, you know what we have in here, it's another square. So the area of this bigger squared is C squared. So now, since these are the same square, I know that their areas are the same. So area of the first square is equal to the area of the second squared. So the area of the first squared is b squared plus, now we have ab plus ab. Those are like terms, so we have 2ab and then plus a squared. Okay, that's the area of the first square. And this is equal to the area of the second square. Now, 1/2 AB, we have AB, 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 and AB. Those are all like terms. And 1/2 plus 1/2 plus 1/2 plus 1/2 is 2. So we have 2AB plus c squared. Okay, so we didn't talk about equation solving yet. However, what we have here is that we have a 2ab on the left side of the equation and a 2ab on the right side of the equation. Those cancel each other out because we have the same thing on both sides. So what we're left with is a squared plus b squared is equal to c squared. And if you notice how I labeled my triangles here, we have right triangles. So A is a leg, B is a leg, and C is the hypotenuse. And we have this relationship, a squared plus b squared is equal to c squared, between those three variables. So that's one proof of the Pythagorean theorem. And there's maybe 1,000 more proofs of the Pythagorean theorem. This is I think it's the most proved theorem in mathematics. So hopefully you could understand that particular proof. It's not too hard to understand if you see where the areas are coming from here. Okay, so now let's go ahead and put this Pythagorean theorem into action and move on to the final example. And as you can see, I have a little sailboat here because we are involving a boat. So we have a boat, sails from Brisbane on the east side of Australia, 40 kilometers east, and from that point 30 kilometers south. So we want to find the boat's distance from Brisbane. Okay, so we have this word problem here. So if we could draw a picture, if you could somehow visualize this in a picture form, that's going to be great. So let's have Brisbane here. So let me just mark it as a dot. So that's Brisbane. And this is where the boat begins, right? So we have our little boat here. You could draw a boat and a flag if you'd like. It's a pirate ship. So from Brisbane, it's going to sail 40 kilometers east. Okay. Now we need to know our cardinal directions in this case. So let me just draw them quickly here. We have north, east, south, and west. Okay. So it goes east, right? So it's going this way. And then it stops. Okay. Now the distance from here to here is 40 kilometers. So let's go ahead and label that. That's fine. Now from this point, we sail 30 kilometers south. Be careful of making the mistake. I've seen people do similar problems where they go like this. But you have to keep in mind that the boat is sailing here. It stops, and then from this point it's going to go 30 kilometers south. So south is in this direction, right? So this is 30 kilometers and it stops here. And then we want to find the boat's distance from Brisbane. Okay, so here's Brisbane. Now the distance from here to here, whoops, no, there we go, okay, is the line from here to here. Now, of course, on the surface of the Earth, you're dealing with spherical geometry. We're not going to have an exact straight line here, but for the most part, with distances this small, yeah, actually, these are pretty large distances, but for the most part, you're going to be close with the straight line. So, for all practical purposes, and just the fact that we want to practice the Pythagorean theorem, we're just going to draw a straight line from Brisbane to the current spot where the sailboat is. Okay, so here's a nice picture. Now the boat's distance would be represented by this line here. We're going to call that D. And if you notice, what we made was a right triangle. That's very important. So we made a right triangle, so we'll be able to use the Pythagorean theorem. So the Pythagorean theorem says that one of the legs squared plus the other leg squared will equal the hypotenuse squared. Now, we did not talk about equation solving yet. So let me give this formula to you in a different manner. Okay. Now, we want to find the hypotenuse, not the hypotenuse squared. Okay. We just want the hypotenuse. So once we do some equation solving, you'll see that we can solve for c by taking the square root of both sides. So this new form of the Pythagorean theorems becomes the square root of a squared plus b squared is equal to c. Okay, so let me just put a star next to this one. This is the formula we'll use here. But again, most people memorize the formula without the square root here. So now, we know one leg is 40. So we square that. We add it to the other leg, squared. We take the square root of that, and we'll obtain d. Now, I would call it c up here, but in our application, I call it d. It doesn't matter what you name these variables here. So now we do the work. We follow the order of operations. Now, there's an invisible set of parentheses in the square root, but that's the only thing that's here. So, of course, we're going to have to work within the square root. We do exponents next. So, 40 squared is 1600. 30 squared is 900. And that's all square root. And this is equal to d. And this 1600 plus 900 is 2500. And this is still equal to d. And lastly, the square root of 2500 is 50. And let's make sure we have the correct units. We're dealing with kilometers. And this is a one-dimensional measure, right? This is a line. So we should have just kilometers. Not kilometers squared. That would be an area. This is just a line. So 50 kilometers is equal to d. Okay. Now, this is one of those, this is called a special triangle. This is a multiple of the 3, 4, 5 triangle. It's 10 times that particular triangle. 3, 4, 5. So that's one way to always create a triangle. Or if you take like 3 times that multiple, it would be 9, 12, 15. But, that's just some special triangles. Those are Pythagorean triples, those are called. Okay, so we have 50 kilometers is the distance, and that's our final example for that boat problem. Okay, so that is expressions and formulas. I hope you enjoyed this video, and I'll see you in the next one.